Hi, everyone. Thanks for that introduction, Alex. Hopefully you've all started to wake up. I'm still 2 hours earlier, so I will be double-fisting my coffee during this talk. My name is Jenny Finkel. I'm an engineer at Prismatic, and I am excited to have this opportunity to share with you how we use machine learning and natural language processing as the backbone of how we do relevance. So given the current audience, it's probably worth mentioning that at Prismatic, we're a functional programming shop. The entire backend is written in Clojure. The web front end is entirely Clojure script. My personal background is academic. I went to graduate school in computer science, focusing on machine learning and natural language processing. And so doing real artificial intelligence work in a Lisp makes me feel pretty cool. We're also very involved in the open source community. You may have caught my colleague Jason Wolf's talk on Graph here last year, or his unsession on schema last night. This talk, however, is not going to be about any of that. So I should probably start out by explaining what we do at Prismatic. We work on what we like to call the discovery problem. And so the problem is this. You're a person, you like surfing the web, you like finding stuff to read, and the web is vast, so it's not that hard to find some content you like. In my case, that probably means cat pictures. It's probably going to be mixed in with stuff you don't really like. In my case, that would be sports articles. But the problem is that there's loads and loads more content out there that you don't see, much of which you would probably really enjoy. And this slide is actually misleading because it makes it look like you see about as much good stuff as you miss, when in reality, you're going to miss out on far more than you actually see. And so, at Prismatic, we try to go outside of your regular sources to bring you lots more content that we think you'll like, but which you otherwise would have missed out on. The virtue of what we do is not taking your Twitter feed or your Facebook feed and reordering the stories in it. Rather, the virtue is in finding you great stuff you would have otherwise missed out on, because it's shared by people who are too far away from you socially, or it's outside of your regular news sources, or it's on the periphery of your interests. To us, this is what serendipity is all about, finding you these gems. A bit more concretely, we provide a personalized news reader. This is the web app up here. And so when we use the term news, we really mean it quite broadly. To us, it means anything that people are sharing or talking about on the web. And so up on this slide is a slice of my personal home feed showing a variety of my interests, like cats, marijuana reform, functional programming, ice cream in San Francisco, and Burning Man, as well as who in my network is recommending the story. So how do we do this? Well, we start off by crawling the social and the open web for engaging content that's being shared. We then analyze and categorize all of the content that we've crawled, and a bit later in the talk, I will go into a bit more detail about what this analysis looks like. And we then serve up the personalized feeds that I just showed you for each of our users based on their network and their social and their interests. So in order to build that really good home feed for me, this is the goal that we must achieve. We want to build a ranker to find a small number of great articles for a user from a large document index. So as you already know from the title of this talk, we use machine learning to solve this problem. I've personally been doing machine learning for over a decade now, and I've noticed that when people discuss machine learning, artificial intelligence, especially to people outside the field, and especially in the context of a business, people are attracted to the idea of a special sauce or a secret sauce. And so in this talk, I hope to convince you that there is no secret sauce, but rather, much like with cooking, is about paying attention to detail and making a whole lot of correct choices. In fact, I think this quote by my friend and boss, Aria, sums it up perfectly. People who use the term secret sauce know about neither food nor technology. If you think about it, it's true. Delicious food does not come from a secret sauce, but rather from fresh, high-quality ingredients, often simply but properly prepared. And for each ingredient, a good cook will understand its strengths and its weaknesses, how it pairs with the other foods in the dish, and how best to prepare it. Similarly, with machine learning, you need to get all of the details right. And the different components of the system have to be assembled together thoughtfully. So on that note, here's an outline of the rest of the talk so that you know what's in store. So first, I'm going to talk about the data that we have to work with regarding both our users and our index of documents. Then I'll discuss some of the constraints that we needed to work within. After that, I'll cover evaluation. How do we even know if we did a good job? At this point, we'll have built up enough information that I can actually explain to you how our system works. After that is my favorite part of the talk, all of the problems that we encountered along the way. Putting a machine learning system into production was definitely a learning experience, since my previous experience had all been academic. Then I'll tell you how our final trained ranker actually performed on real users, and then there should be some time at the end for questions. So let's get started with what data we have to work with. We have a lot of documents. We don't have Google-scale documents because our goal isn't to operate over every page on the web. Instead, we want recent documents of a more timely nature, like I said earlier. Our crawler considers many millions of pages every day, but allows under 1 million into our index at a time. Documents expire from the index once they get too old, which to us means when users stop interacting with them. And so our index is constantly changing over, and it entirely changes over about once a week. Each document that enters our index goes through a lot of processing. Looking at this snippet from my home feed, you can actually see most of the information that we have about each article. Each document has a publisher. For this article, it's Car Throttle. We have hundreds of thousands of publishers in our system. We also extract the author of each article. Intuitively, this seems like useful information, since perhaps you have a preference for a particular writer on a particular site. I know that I do. Next up, you see the age of the article. It turns out that date extraction is actually quite tricky for us. Some documents will have open graph date tags, and it's great when they do, and we certainly use them. But oftentimes, there's no metadata to rely on, and so we have to extract the article date ourselves. And it turns out that articles actually tend to have lots of dates in them. There's when the article was written, when the article was updated. There's all the dates on all the comments in the article. There's the date in the URL sometimes. And sometimes, just for fun, I think, websites will display the current date and time. And so for a while, we punted on this and just used the date that we fetched the article. But eventually, we built an in-house data extractor. And though it's imperfect, it's still quite accurate. Documents also get labeled with topics. So for this article, it's cars and automobile design. I want to go into a little bit of detail here about our topic classifier. So our topic classifier can classify articles into over 5,000 documents, and we're actually about to do a major expansion to extend that list by orders of magnitude. Documents can be labeled with multiple topics, and the classifier will give a degree of confidence for them. These are the same topics that our users can add as interests, and which help determine which articles we show them. The topics are a critical component of our system for many reasons, including the ability to explore new interests, which is something we want our users to do. So when we show you the topics on an article, we don't just show you the topics that you're subscribed to, but all the topics that we can fit into the space provided. This becomes a way to expand out from a current interest into new related interests. I wish I had time to go into more detail about how we actually built our topic classifier, but there's not time in this talk. But you can certainly ask me about it later. So let's get back to the article. If you shared your Twitter or your Facebook OAuth with us, then we know what articles your friends are sharing. And because we have lots of people's OAuth, we generally know what's being shared a lot. And while we don't necessarily want to show you everything that's been shared by all of your Twitter or Facebook friends, clearly it should be a useful indicator. For each article, we also know all of the actions performed by Prismatic users who viewed the article on Prismatic. The full set is click, like, which we also call recommend, save, share, as in share via email or share out to Facebook or share out to Twitter, and remove, which is when you X out an article that you don't like. Only some of these actions are publicly viewable by other users, but we can learn from all of them. We also pull out the title of the article and the text, and we can look for key informative terms. These are the ones with high TF, IDF, if you know what that means. And these terms can help give us a fingerprint of what a story is about. We also have information about our users, which we fully utilize. Prismatic users can follow one another, and obviously, we know all of the people that you follow on Prismatic. And so if several of them like a story, we should be more inclined to show you that story as well. Users can also add topics and publishers to their favorite interests, so we know what your stated interests are. Next, we have recorded information about each user. We maintain long-term summary statistics for every topic or publisher that every user has ever interacted with. You can view it as a summary score. If I've removed a lot of articles from Thought Catalog, then Thought Catalog should have a negative score. If I click on a lot of cat stories, and I do click on a lot of cat stories, then the cats topic will have a high positive score. Obviously, this information should be useful for picking stories for a user, particularly in the case where there's an interest that a user clicks on a lot but has not added to their favorites, or if there's a source that a user has removed a lot. Lastly, we have saved off session data. We snapshot every session that a user has, and we save off the articles that were shown to the user and the order that they were shown in. We also save what actions the user took on which articles and the user's state at the beginning of the session, including what interests they have as favorites and what their interest scores were. One thing that's worth noting, and will come up again later, is that when we generate a feed, we often generate far more articles than the user actually scrolls through. And so for the articles that they didn't reach, we can't know how they hypothetically would have interacted with them. And so we only save off session information through the articles that the user actually scrolled through. So next, I'm going to talk about some of the constraints that we need to work within. We make each user's personalized feed on the fly so that we can provide you with the highest quality and most up-to-date feed possible. This also means that the API call to get a ranked feed is a user-facing call and must be done very, very quickly, on the order of a couple of 100 milliseconds. The set of documents that we will consider showing a user is based on their interests and their social network. And so it's not the entire document index, but it is a very large subset of it. As I'm about to get to, we do the ranking by giving a score to each of these documents for the current user. And then we sort by these scores. Given that, we need each score computation to be lightning fast. We also have to deal with the fact that what users claim to like and what they actually like are often quite different. I think users' favorite interests are often aspirational, in the same way that they are on dating websites, where everyone claims to like hiking and cooking and reading, and no one claims to enjoy getting stoned on their couch, eating potato chips, and watching trashy reality TV. I really like these pictures. So lastly, and sorry to state the obvious here, but different users are different. We hear both, my friends are idiots and I don't care about what they share, and all I want is a forum to discuss stories with my friends all of the time. The reality is, some people want more topic-based content, some people want more social-based content, and most want a mix of the two, but to varying degrees. And so we have to invisibly deal with all of these conflicting desires. So before we get to how we actually do it, we need to answer an important question, which is how do we even know if we've done a good job? So the true objective is improved user engagement. Are users coming back more often? Are they generally having a better experience? But the first problem with this metric is that it takes a long time for user behavior to change. And it takes even longer to confidently measure that it has changed. If our development cycle depended on measuring user engagement, it would take weeks to evaluate a ranker. And we need to be able to iterate much more quickly than that. We also can't do machine learning on standard engagement metrics because we need information about which specific articles the user did and did not like. So instead, we need something that we can calculate offline from that raw session data that we saved off that I told you about earlier. But of course, we have to believe that our metrics are a good surrogate for user engagement. So instead, we ask ourselves, are people interacting more? Are they reading for longer? Are they removing fewer articles? And based on the belief that more interaction is correlated with a better experience, we came up with a set of interaction-based metrics that we use to evaluate a model. These metrics will give a better score if there's more good articles, so articles the user clicks on or shares, and they're higher up in the ordered list. And if there's fewer bad articles, those are ones the user X's out, and they're lower down in the list. We can use these metrics, along with our saved session data, to quickly iterate offline by splitting this data into training data and test data. Initially, we squirrel away the test data, and we don't look at what users interacted with in those test sessions. We develop a model using only the training data. We then take the users and the articles in the test sessions and use our newly trained ranking model to reorder the articles, hoping that the ones the user interacted with positively will float to the top of the ordering, and the ones that the user removed will move to the bottom. OK, so now we can get to the good stuff. And I can describe to you how we actually built our relevance system. So how do we turn this into a machine learning problem? Well, we can look at people's old sessions, and though, like I said earlier, we can't know anything about how they hypothetically may have interacted with the stories that they didn't scroll to, we can learn a lot from how they interacted with the ones we did show them. So to do this, we build a model of article user interactions, such that for an article user pair, we predict how positively or negatively that user is likely to respond to that document. Our first step was to collect data. This is more than just user-article interaction triplets. We need to know the state of the world at the time the user saw that document. What were the user's favorites? What were the user's per topic and per publisher interaction scores from previous interactions? What was the social activity on the article at the time we had to make a decision? All articles will start off with no prismatic activity, and so we need to learn to identify promising stories even if there's no activity on them. Here is a visual representation where one session log gets transferred into many data, and where each datum includes the article, the user, and whether it was a positive or a negative interaction. Next, we need to come up with a set of features for these data. These are basically questions that we can answer programmatically about article user pairs. They should be based on facts, which should help you determine how likely a user is to like or dislike a particular article. Here are some examples. Does the article have any topics that the user follows? If so, the feature value is 1. Otherwise, it's 0. Other good features are things like the number of times the user previously clicked on documents from this publisher, or the number of times the user previously removed articles from this publisher, whether or not the article has a picture, or the number of other Prismatic users who have liked the given article. All of the content analysis that I showed you earlier is used in these features. Authors, article age, topics, publishers, all of that stuff gets translated into features like this. Once we have the feature values, so these are just the numbers, we can now represent this datum as a vector of numbers. So now that we have these features, we want to learn weights for them. This is the learn part of machine learning. A positive weight should indicate that this feature means that a user is more likely to like an article, and a negative weight should indicate that this feature means that a user is more likely to dislike an article. The magnitude of the weight should indicate how big of an impact that feature should have. We then take these feature values, which we computed from the user and the article, and the feature weights, which our ranker has learned, and I'll describe more very shortly, and we compute their dot product. This gives us a score for the user-article pair that tells us overall, in summary, how much we think the user will like or dislike this particular article. So our goal then is to find the best possible values for these weights. We use a model called logistic regression, for those of you who are familiar with it. Basically, we want to find the weights which cause the positive examples, that is the good articles, to have large positive scores, and which cause the negative examples, the bad articles, to have large negative scores. Getting back to our visual representation, you can now see that each of these data is transformed into simply a feature vector of numbers and a positive or negative for whether it represents a positive or negative example. Depending on the weight vector that we use, we can now compute scores for each of these data. Here's one set of possible scores. You can see that for the first and the last data here, the scores line up properly with whether it's a positive or negative example, and that the two in the middle are mismatched. This means that for this particular set of weights, our ranker would think that the user is likely to enjoy the second article and dislike the third article, when in reality the opposite is true. There are an infinite number of possible weight vectors that we could choose from. And we want the one that gives the green data the highest possible positive score, and the red ones the lowest possible negative score, like this. So how do we actually find these weights? We use numeric optimization. Do you remember when you took calculus and you learned how to find the maximum of a function by taking the derivative and then finding the point where it equaled 0? Well, this is that, but just with thousands of dimensions, one for every feature. And so the optimization determines how the different features get traded off between. Is a social signal worth twice as much as having a topic in common? Or is topics in common more important? Instead of just guessing, we find the mathematical optimum. So now we're on to step 4, classifying new data. I need some coffee. On one level, classifying new data is trivial. A user comes to the site, and we compute a feature vector for that user and every document, or every document posts some sort of filter. And then we get scores for that article, and we sort. But there is a problem here. Earlier in the talk, I said that we need this call to return in several hundred milliseconds. And if we need to construct a new feature vector for this many documents, a new object, we're going to be hosed before we even begin. So instead, we do some algebraic manipulation. In our original formulation, the one that we actually use when training offline, and that I've been describing to you thus far, the weight vector is user-specific, but the weights themselves are universal. However, we constructed the features so that the ones which are user-specific can actually be constructed from other features which are only over the document. This table on the top shows 3 features. The first 2 are about topics on the article and have nothing to do with whatever the current user is. The last feature is user-specific, but it is closely related to those first 2 features. In this case, let's assume that I do have cats as a favorite interest, but I do not have photography. So what we do in our faster formulation on the bottom is we remove the user-specific features, and instead we manipulate the weight vector to be user-specific. In this case, that means that we would update the weight for the article has the topic cats feature by adding in the weight for article has a topic that the user favorited, because the user has cats as a favorite topic. The weight for article has topic photography does not get updated, because I do not have photography as a favorite. Because of this transformation, when new documents enter our index, we need only compute this static feature vector. And then all we need to do to score documents when a user comes into the site is to do this one weight transformation, and then we can do a fast dot product on all of the documents with no expensive object creation. So the cycle that I described in the first 3 steps is shown in purple here. We can train a model, we can evaluate it on our saved data, and then, based on the results of that evaluation, we update the model, usually by adding more features. This cycle is very fast because it operates entirely on saved off-session data. It also doesn't require us to use live users as guinea pigs. However, once we have a model whose offline performance we are happy with, we will want to deploy it to live users to see how it does. This is the cycle drawn in red. This cycle is much slower, so we have to spend most of our efforts on the purple cycle and only deploy to real users when we feel confident with the current model. The red cycle is very, very important, though, because when we deploy to real users, things often don't go as expected. Which brings me to my favorite section, which is the problems and the stumbling blocks that we encountered along the way. So I'm going to discuss each of these 5 issues that we ran into one at a time. So when we first deployed our first trained model to production, we were super excited. According to all of our offline metrics, this new ranker was substantially better than what had previously been up on prod. We were ready for showtime. Of course, we didn't want to deploy the new ranker to 100% of our users right away. So some sessions were ranked by the old model, and some by the new model, so that we could compare between the two. Well, our excitement quickly turned to disappointment when the numbers started rolling in. Our new ranker was doing a lot worse than the old one on all of our interaction-based metrics. We started investigating, and we noticed that the weight that we had learned for a publisher match interest score, so you have an interest score for the publisher on the document, was a lot higher than we'd expected. We figured it would have a positive weight, but a much smaller positive weight. This didn't pass our intuitive smell test, and we suspected that we probably had a bug somewhere. Since our code for saving off the session data was much newer than our core machine learning code, we looked there first and we found our bug. When we were saving off session data, if a user interacted with any articles during the session, the updates to that user's interest scores were happening before we snapshotted the session and not after, like it was supposed to be. The effect of this is really, really bad. What happens is this. So like I said earlier, we have hundreds of thousands of publishers. This means that a lot of articles that we show a user will be from publishers they have never interacted with before. And oftentimes, when a user clicks on an article, it will be the first time that they clicked on an article from that particular publisher. At the top here, you can see what the feature value should have been in the case of a clicked-on article from a previously unseen publisher. Below that, you can see what it actually was when we were training the model. Every single document that a user had clicked on would have an interest score for that article's publisher. And as a result, the numeric optimization process was inadvertently exploiting this bug, and it learned a really high feature weight. When we were evaluating offline, the data had the same bug, and so it looked to us like we were doing really well. But when we then deployed this ranker, it was placing way too much value on the publisher, and this was causing, poor results for our users. This is pretty typical for a machine learning bug. Your code doesn't crash, there's nothing blatantly wrong that you can just go in and fix. Instead, the data just seems kind of off, and you have to think about it a lot and use reason to figure out where it came from. Next up is presentation bias, which is the fact that users are a priori more likely to click on earlier articles, and especially the first article presented. Search engines also suffer from this problem. It's annoying in several ways. Our learning algorithm is based on the assumption that when a user has a positive interaction with a document, it's because of something inherent to that article, and not something external like that article's location in a list. So this leads to noisier input training data. It also makes live rankers look better than they are, since people are inclined to click on earlier articles presented regardless of quality. There's really not a whole lot you can do about this other than to just be aware of it. Next up, I want to talk about a problem that we encountered specifically because we were doing ranking instead of normal machine learning. Most machine learning algorithms, including the one that we used, are based on the premise that the training data and the test data are drawn from the same distribution. Unfortunately for us, at training time, we only know about the 50 or so documents that the user actually viewed. But when used in production, we generate thousands of ordered documents. What this means is that the 50 documents that we are looking at are the ones that we already had reason to think are pretty good, because they were the 50 highest ranked articles for that user by whatever the previous ranker was. This means that we learn from only a small fraction of the documents that were presented to the user. But when we have to guess what to show the user, we guess from the entire collection of documents, and the two look very different. This can lead to pathological behavior, which I will explain with an example that we actually experienced. And for those of you who are users, you may remember this phase, because we got a lot of complaints. So the Daily Mail writes a lot of stories every day, and they get tweeted and they get shared on Facebook a lot. But it turns out that our users don't really like the Daily Mail. And so the ranker that we started this whole process with rarely served up Daily Mail articles. And so for a Daily Mail article to end up in a user's feed, there had to be something really special about it. It had to actually be a good Daily Mail article. And so the user was more likely to click on it. But so then what happens the next time that we train a ranker? We find that there are not that many Daily Mail stories, since we only train documents from the small green circle, that when there is a Daily Mail article, they have a high click-through rate. And so as a consequence, we learn a high weight for the Daily Mail. Well, we deploy this new ranker with a high Daily Mail weight, and now we're showing everyone Daily Mail up the wazoo. And so they start removing the Daily Mail articles, remove, remove, remove. And then the next time that we train, the model, we learn that the Daily Mail always gets removed, and we give it a negative weight. And so now we're right back where we started, and the cycle continues. This is one example, but really it ended up happening for all sorts of different features, because our training data and our test data are inherently different. We can't totally fix this problem. We ended up alleviating it by removing raw publisher features and other very specific features like them. However, because we still have features based on interest scores, if a particular user clicks on the Daily Mail a lot, we will still learn to show that particular user Daily Mail articles. So this one was fun, statistical bleeding. So usually, we have multiple rankers running at the same time for comparison. One common situation where this is the case is when we have an existing ranker and we want to test out a new one to potentially replace it. And when we do this, we'll slowly ramp up the fraction of users that get the new ranker over the course of a week or two. For the sake of simplicity, let's assume that one ranker is all about exploration, represented here by the painting of Lewis and Clark. It's got a decent likelihood of showing users brand new articles that have no activity, hoping to find undiscovered gems. In this scenario, the second ranker is all about exploitation, represented by the businessman who's eavesdropping on Lewis and Clark. The exploiter keeps showing users the documents that have a lot of positive interactions already, figuring they are good articles and people will probably like them. You guys see where this is going? If you have 90% of users on the explore ranker and 10% on the exploit ranker, the explore ranker will unearth all of the good articles, and only then will the exploit ranker take these documents under consideration to show people. I've drawn an example up here to show how the information gets passed between the two rankers. You can see that when a new article comes in, the exploiter won't show it to anyone, because it has no activity, but the explorer will. And let's say that this new article is a good one, and so the user clicks on it. This causes the statistics on the article to get updated, which the exploiter also has access to. Because the exploit ranker can see these statistics, it knows that it is a good article, and so it will show it to other users. The exploit ranker will probably do pretty good in this scenario, since it's making the explore ranker do all of the hard work. If the explore ranker was the old ranker, and the exploiter was the new one that we were considering switching over to, the exploit one would be looking pretty good right now, and we'd be cranking up the fraction of users who are on it. But what happens? Well, eventually the exploiter is the only ranker, and there is no one to do the exploration. And so the exploit ranker will just keep showing users the same sad couple documents over and over again and never get any better. Based on how strongly weighted the activity and the social features are, this is an exaggerated version of what really happens. And so we have to be mindful to keep retraining as we crank up the number of users who are switched over so that the model learns over the correct inputs. All right, I saved the best one for last. How many of you know what Simpsons Paradox is? Any? A few. So this is the Wikipedia example that I found to be most intuitive. In the 1970s, UC Berkeley was sued for bias against women who had applied for admission to graduate school there. The admissions figures for fall of 1973, shown here, showed that men were much, much more likely to be accepted than women, and the difference was so large that it was unlikely to be due to chance. But when examining the individual departments, it appeared that no department was significantly biased against women. In fact, most departments had a small but statistically significant bias in favor of women. The data from the 6 largest departments are shown here. So what's the explanation? What happened was that women tended to apply to competitive departments with low rates of admission, even among qualified applicants, whereas men tended to apply to less competitive departments with high rates of admission among qualified applicants. And so in summary, it looked like the women were being discriminated against. But in reality, the different departments did not have the same acceptance rates, and women tended to apply to the departments that accepted fewer applicants. The same thing happened to us. We were super confused at first. When we were looking at live results, we often break it down like this. We'll be comparing two rankers, and we'll look at both summary information as well as how each ranker did on each of our two platforms, iPhone and web. One day, we were looking at results, and we realized that ranker 1 did better in summary, but ranker 2 did better on both of the individual platforms. So we were super confused, but my colleague Jason was the first to propose that it might be an example of Simpsons Paradox, and he was right. What happened was that we would shift the percentage of users who got each ranker. And because users are more likely to use the iPhone at some times of day and more likely to use the web at others, it ended up that more iPhone users had sessions with ranker 1, while more web users had sessions with ranker 2. This combined with the fact that overall, people are more likely to click on articles when they're on the iPhone than when they are on the web. And so, because iPhone users click more, and more of them got ranker 1, this corrupted the summary statistics to make it look like ranker 1 was better, when in fact, ranker 2 was better. After this, we started resetting data collection every time we changed ranker percentages. So on to some results. So I never really explained to you what our original ranking model looked like before we switched to our machine learning model. And I'm not going to go into much detail about it now. But basically, some little small parts of it were learned, but mostly it was just a hand-tuned model over a small number of features. And so here you can see how the current live ranker that we have up on production right now performed compared to the original ranker. Users are sharing about 50% more. There's a 25% higher likelihood that a user will click on the first document. So even with presentation bias, that's still clearly a huge win. Users are staying longer. Sessions are about 15% longer. And lastly, we have 15% fewer total crap sessions, which means a session where a user doesn't click on anything, share on anything, do anything. They just kind of scroll and peace out. And so overall, we're super happy with these results. And so here's a little summary of everything that I've told you so far. So we collect information about our users' preferences and dispreferences, both explicit, which is the favorites that they've added and the people that they follow, as well as implicit, which is what stuff do they actually click on. We analyze all of the articles in our index to understand what they're about. So this is the topics and the publishers and the key informative terms and the date in the article, all of that. And then we snapshot the user sessions that we're actually going to do the direct learning on. From those sessions, we extract features, which are meant to be hints that should help us decide if a user will like an article or not. We then learn weights for these features, which determine how the features trade off between each other, and how we learn which features are more valuable and which features are less valuable. And then we use these weights to rank articles for a user. And then lastly, I want to thank the rest of the Prismatic backend team. Relevance at Prismatic is not a one-woman show. The entire backend team worked together on our relevance model. Jason Wolf is here in the audience, and that's strangely if you guys should go try to talk to him later. And the rest of the team was Dave Goland, Arya Hagigi, and Ian Wong. And that's it. Thanks for listening, and I think we got about 10 minutes for questions.